Chandrayaan-3's newest find has caused ripples in the international science world. What started as a well-executed mission to showcase India's ability to pull off a precision soft landing on the lunar South Pole is now one of the greatest planetary discoveries in recent history. Vikram lander and the Pragyan rover made a descent so accurate that ISRO engineers likened it to threading a needle while standing on the other side of a football field. But when their landing telemetry and imagery were scrutinized in the following days, it was apparent that the touchdown location was very far from a typical lunar surface. What Vikram and Pragyan had themselves landed on was, in reality, the bottom of a giant, ages-long dug-up impact crater, an edifice so old and so huge that its entire history had been concealed for billions of years. By using navigation camera images and cross-referencing with the moon's prior high-resolution orbital photos, mission scientists located a half-circle depression about 160 kilometers across and dropping over 4 kilometers deep at its initial creation. To put it in perspective, were it positioned on Earth, this unseen basin would run from one large metropolitan city to the next, engulfing everything in between in a bowl-shaped wound. Still more remarkable was its age. Initial geological modeling indicated the crater was older than the already gigantic South Pole, Aitken Basin, itself one of the largest and oldest impact craters in the solar system. This indicated that this newly discovered feature was not merely another lunar crater, but a remnant from the moon's earliest eons, birthed when our world's celestial companion was still radiating from the heat of its birth. For eons beyond counting, heavy blankets of ejecta from subsequent impacts had crept over it, leaving barely a whisper in surface elevation charts. Chandrayaan-3's descent cameras, with their skewed views and outstanding resolution, had inadvertently stripped away that curtain. The method of verifying this discovery was arduous. Researchers superimposed computer models of elevation onto the unprocessed descent video, laboriously drawing the ghostly curve of the rim of the crater. Despite erosion by micrometeorite impacts and space weathering having gentled its edges, the curvature was unmistakable. From hundreds of kilometers across, the ground subtly rose, not sufficiently to be noticeable on the surface, but evident from overhead. Its sheer size was only realized when mosaicing photos taken both by Chandrayaan-3 and lunar orbiters. It's like suddenly realizing you've been standing in the center of a stadium the size of a small country, remarked one planetary geologist involved in the mapping effort. What lay within the crater's fill was equally tantalizing. Geological models suggested that the material here was likely excavated from deep within the moon's crust, possibly even from the upper mantle, during the colossal impact. Across billions of years, this depression had served as a geological time capsule, maintaining rocks and minerals unaltered since the earliest pages of lunar history. The Pragyan rover, while range-constrained, may be able to analyze boulders or ejecta fragments that came from depths unavailable anywhere else on the moon. If mantle minerals were found, they might provide fresh evidence for the moon's differentiation, the chemical constitution of its ancient magma ocean, and the chemical signatures of its violent origins. But the significance of this find is not entirely scientific, it is practical and warning. Hidden craters of this size can harbor hazardous environments. The regolith over them can differ radically in thickness, concealing cavities where broken rock has moved over millennia. Such regions can represent genuine threats to prospective landers, rovers, and particularly human settlements. Stability evaluations of lunar bases might now involve not merely surface mapping, but deep penetrating radar surveys to verify the Earth is structurally stable. The discovery has already triggered debate among mission planners at NASA's Artemis program, China's Chang'e team, and a number of commercial space ventures. The selection of a landing site on the moon's poles, previously considered largely a matter of lighting levels and proximity to ice, will now also be a matter of staying away from ancient, fragile crater basins. But the underground crater was just the beginning of a flood of discoveries by Chandrayaan-3. Shortly after landing, Vikram's package of scientific gear started sending out heat readings that provided further evidence for extensive, accessible ice reservoirs beneath the moon's polar regolith. By drilling just 10 centimeters into the surface with its temperature sensors, the lander measured extreme fluctuations, blistering daytime temperatures well over 80 degrees Celsius when the sun's rays hit directly, dropping to bone-chilling nighttime temperatures close to -170 degrees Celsius under lunar night. These readings verified that some shadowed areas are subject to cold trapping, circumstances in which temperatures are never high enough to cause frozen water to sublimate into vapor. The biggest revelation was just how small a slope is required to achieve such conditions. Modeling from Chandrayaan-3 data indicated that slopes that face away from the sun by only 14 degrees or so would be able to preserve subsurface ice for billions of years. This wildly expands the number of places where exploitable ice may exist, but makes the engineering problem of how to get it much tougher. The existence of ice on the moon is a curiosity only. It is the most valuable natural resource for extended lunar exploration. Ice can be warmed for water to drink, broken down into hydrogen and oxygen for rocket propellant, and employed to produce a breathable atmosphere. It would also make a potent radiation shield when deployed around habitats. But Chandrayaan-3's results indicate that much of this ice is likely to be in the form of a complex mixture with lunar soil, or in the form of fine grains spread throughout regolith, much harder to harvest than plain blocks of frozen water. As scientists were absorbing these thermal surprises, another surprise surfaced in Vikram's sensors, this one rattling the moon's image as a dead world. The Instrument for Lunar Seismic Activity, ILSA, recorded over 50 seismic events during the mission's surface operations, none of which could be traced to rover motion or equipment operation. Several of these moonquakes lasted more than 10 minutes, much longer than normal microseismic events observed in earlier missions. This also posed a first question: what was behind them? The moon lacks dynamic plate tectonics like those of Earth, but is far from static. One theory is that immense temperature fluctuations between lunar day and night make the crust expand and contract, creating stress fractures. Another is that the moon, stuck in tidal lock with Earth, flexes ever so slightly as it goes around the planet, producing very small but detectable quakes. A third, and quite fascinating, alternative is that these quakes are associated with slow settling in the ancient crater basins, conceivably even within the buried crater itself that Chandrayaan-3 had been on. Whatever the reason, the consequences are apparent. The surface of the moon is mechanically active in ways that may impact both robotic and human infrastructure. Buildings constructed without due consideration of such vibrations may experience cumulative damage over time. This is bound to result in new standards for building on the moon, including flexible foundations, shock-absorbing materials, and ongoing seismic monitoring networks. Together, the buried crater, the ice map, and the seismic activity reveal an entirely new picture of our natural satellite. The moon is not just a peaceful, airless boulder drifting in space. It is a world with hidden wounds from unimaginable collisions, reservoirs of ancient ice ready to be tapped, and a crust that continues to groan with motion. To scientists, they are thrilling results, each one pushing at the edges of current models and unveiling new research possibilities. To engineers, they are critical alerts to the environment that future missions will have to weather. And for policymakers, they reinforce the importance of thoughtful planning, resource allocation, and global cooperation. From a planetary science perspective, samples from the buried crater potentially could be the jewels of lunar geology. If mantle rocks are proven, these may expose isotopic signatures that can pinpoint the age of the moon formation and its early thermal history. Comparisons with Apollo, Luna, and Chang'e mission samples might indicate how the different regions of the moon evolved under different histories of impacts. Such information would not only further our knowledge of the moon itself, but also give analogs for other rocky worlds' evolution, such as Mars and Mercury. Already, the ripples are being seen across the community of space explorers. NASA has said Artemis missions will have more sophisticated ground-penetrating radar equipment to search for buried buildings before crew deployment. China and Russia are eyeing a cooperative lunar seismic network with instruments at several polar locations to triangulate quake origins over periods of months and years. Private companies that develop landers, as well as mining startups, are going back to the drawing board to include more sophisticated surface conditions into their business models. Outside the labs and mission control facilities, Chandrayaan-3's findings have ignited the moon's position in the human imagination once again. For decades, the general perception of the moon was influenced by low-quality Apollo imagery and the romantic idea of a quiet, timeless world. Now, that picture is giving way to one of a dynamic, dangerous, but resource-laden frontier, a frontier still keeping some of the solar system's earliest secrets. The realization that we have only scratched its surface, quite literally, gives new urgency to continued exploration. Strategically, lunar geohazards are currently being viewed as possible national security issues. A country building structures on unstable terrain runs the risk of disastrous failure, not only for its own operation but for common facilities or communication systems. Educationally, the results provide rich soil for STEM activity. Students can simulate the thermal environment that maintains lunar ice, model the crater impacts in physics labs, or engineer quake-resistant lunar structures in engineering classes. There is also an ethical consideration. The Moon's geological record is a resource of planetary heritage, and its earliest features are irreversible. As debate about mining and resource extraction becomes louder, so too must become the call for treaties that safeguard scientifically valuable places. Chandrayaan-3’s buried crater, especially, is potentially going to be a test case for how humanity reconciles exploration and conservation. Ultimately, Chandrayaan-3 has accomplished so much more than a textbook-executed landing. It has broadened the knowledge of our origins, compelled us to redefine how we will live and work off Earth, and reminded us that even in our own cosmic backyard, there remain secrets to discover. Under the Moon's still, dusty face is another universe of secret chasms, ancient brutality, and restless Earth, a universe that will challenge our ambition and our prudence as we take our next steps into the stars.